Hello, and thank you for coming to our presentation. We are a research team with University of California, Berkeley, and we'll be discussing our research on evaluating the use of machine learning strategies to predict daylight performance. I'm Valerie Green, and will be giving this presentation along with Ben Taube. We worked on this project with Luis Santos, who is now an assistant professor at Kent State University, and we're under the direction of Louisa Caldas, who is a professor of architecture at UC Berkeley. In this work, we investigated the use of different machine learning approaches to predict daylight performance in spaces with a single overhead skylight. We compared multiple machine learning techniques with the goal of determining which one best predicts a luminance-based and climate-based daylight metrics in our study space. We explored these techniques with the goal of proposing future applications for machine learning to be used as a tool for designers in rapid prototyping of daylight designs. In the first phase of the study, we produced sets of daylighting data to test our machine learning algorithms on. To produce daylight datasets, we ran a series of parametric daylighting simulations using the Diva plugin for Grasshopper. Each study used the same 8 meter by 10 meter room with a single overhead skylight. For each run, the height of the room and the location of the skylight were varied using a pseudo-random number generator in Grasshopper. For half of the cases, we used 3 skylight parameters, width, length, and depth, to vary the skylight geometry, creating what we referred to as box skylights. For the remaining cases, we used 7 parameters to create the pyramid skylights shown on the right. Each parameter was randomly varied between our set minimum and maximum values with a step size of 5 centimeters. We further constrained the parameters to avoid geometric issues such as skylights overhanging the walls or the pyramid skylights being larger on the top than at the base. We ran 20,000 cases to create our daylighting dataset. This was split into sets of 5,000 cases to cover each combination of box or pyramid skylight with a luminance-based or climate-based metrics. For luminance-based simulations, we recorded daylight factor at each of the 220 sensor points in the model, each at a height of 0.75 meters. For climate-based metrics, we used the same sensor configuration and recorded the 6 climate-based metrics listed in the table while simulated using Phoenix, Arizona climate files.
The 4 machine learning models we used were Ridge and Lasso, which are both linear models, K-nearest neighbors, which is a clustering algorithm, and multi-layer perceptron, a type of artificial neural network. The Ridge, Lasso, and K-nearest neighbor models performed poorly. Given that Ridge and Lasso are both linear models, the results suggest that a linear model would not be suitable for this task. The performance of the 2 linear models, Ridge and Lasso, was practically identical. The difference can only be seen by moving out several more decimal places. Although the loss function for Lasso allows for regularization coefficients to go to 0, that was not a significant factor, suggesting that all the factors were important in the model. The K-nearest neighbors model performed well at predicting missing values withheld from a single case, but it was not able to extrapolate to new cases for which it had only the information about the parameters. The multi-layer perceptron models proved to be much more precise and accurate at predicting both daylight factor and the annual metrics than any of the previous models. However, the models were not perfect and required some post-processing of output data. The model predicted some values slightly below 0 and above 100. We changed the negative values to 0 and the ones above 100 to 100, since both daylight factor and climate-based metrics range from 0 to 100. A more robust model with a larger training set may be able to better understand the domains of the target variables, thus only predicting values within the real domain. The R-squared values summarized in the table reflect the R-squared after we made those adjustments to the predicted values. These figures show that the artificial neural network was able to predict daylight factor very well, especially for the box skylights. As more parameters were introduced in the pyramid skylights, the performance of the model went down slightly, but it is still very strong. The model was not able to predict all annual metrics equally well. As shown in this figure, the model predicts daylight autonomy, autonomous useful daylight illuminance, and underlit hours much better than it predicts the other variables. Similar to what was seen on the previous slide, the performance of the model went down when additional parameters were added in the case of the pyramid skylights. In addition to the 20,000 parameterized cases used to train and test the models, we created 3 design cases that we used to further evaluate the tool's application in the design field. The first 2 cases, shown in the top and middle rows, have the same pyramid skylight located in 2 different places in the ceiling, and the third case, shown in the bottom row, has a long narrow light well located flush against the wall. On this slide, we have a comparison of the DIVA simulated daylight factor and daylight autonomy compared to our predicted values. The daylight factor predictions are much more accurate than the daylight autonomy predictions for each case, which we believe could be because the daylight factor is purely a continuous variable, while daylight autonomy is a variable classification of illuminance. Of the test cases, case 3 has the worst performance. Because all combination of x and y coordinates were equally probable in our training set, there were likely very few cases with the light well adjacent to one of the walls, meaning our model did not have enough data to learn this condition. In conclusion, the multi-layer perceptron neural network was the most effective learning algorithm we tried. We see a potential application in accurate prediction of daylight metrics without having to run a simulation. This also yields the potential of building specific, tailored predictive models that users can interactively query and obtain instantaneous performance feedback in top lighting design tasks. We plan to apply these findings to an intelligent brush painting tool for defining daylight goals for goal-oriented design. Thank you, and feel free to contact our team if you have any further questions.